I believe in the audience, there are not many, mostly our major student, right? There are not many second major students, I guess. For the minors, for this CHS, we introduced 3 new minors: minor in astronomy, minor in meteorology and climate science, and physics in technology minor. Unfortunately, among these 3 minors, only the meteorology and climate science is allowed to be taken by primary physics major student. The minor in astronomy and also minor in technology, physics in technology, are mainly designed for non-physics student. You can take the module if that's allowed. I think most of the module in minor in astronomy is allowed to be taken by physics student if you're interested, but of course you're probably going to get bored. If you are interested in astronomy or astrophysics, you should take the specialization in astrophysics for a primary major. If you're a secondary major, then you are allowed to take that minor. For the physics in technology, the situation is similar. We propose a few new modules, which is sort of like a non-tech version of the module we already have. For example, there is a module in quantum technologies, and we have a specialization on quantum technologies. That new module is not for that specialization, rather is for the minor. So it is mostly introducing non-physics majors, how physics is important in the technology world today. Again, primary major is not allowed to take that because they're too easy. And you can tell how easy it is. For example, the minor in astronomy, the required module, maybe since nobody share anything, let me share a website, our physics department website. Okay. For example, in minor in astronomy, the essential module start with a general education module. So that set the tone of how serious or how mathematical this minor is. That's also why for physics majors are not allowed to take this. You skill the grading and all this, etc. But you are okay to taking these modules if you like, interested in those area. But mostly you will be using your unrestricted elective because these modules cannot be used to count towards your major requirement. So that's one thing. Another thing is I want to, all other module minors, other than the minor in physics, obviously, all other minors are allowed to be taken by physics major student. For example, you can take a biophysics minor and you can take a medical physics minor. Medical physics minor will require an interview after application. So in that sense, it's restricted. You not just freely declare. You need to, I want to do this, then my colleague will interview you basically to check what's your intention and what's your background. Minor in meteorology and climate science. This is a new minor, which is also open to physics. Actually, this minor are targeting physics student because this minor will provide expertise in this area, which Singapore probably need in the near future. So that's the reason we open this minor, because we have this need in the people with these skills. And the same goes to medical physics minor. There was a medical physics mastering program, and Singapore has a need for the people to understanding medical physics. For example, to operating X-ray machine or to operating MRI, the magnetic imaging MRI machine, MRI. Magnetic resonance imaging And to understand the physics behind it, you're not just pushing the buttons. If this is a faulty, then what do you do about it? You really need a lot of physics about. And these two are the miners, not heavily subscribed, but we open these miners for the Singapore job market. So therefore, if you are interested in working here right after the bachelor degree, you should consider these two. Okay. Minor in nanoscience now is open to physics major as well. You can have a minor in nanoscience, and you can also specialize in nanophysics. Nanoscience is a combined minor with physics and chemistry department. So you can see half of the module are chemistry, and also some of the modules are specific in this minor. Some modules are shared with the nanophysics specialization, and not even with, let me click here. You can see the modules. And here, for example, if you're a physics student, you already have a gateway module, then you should take the chemistry gateway module. So this physics gateway module will be double counted towards your physics major and this minor. And there are other two modules which are designed for this minor. And in the higher elective ones, you either do UROPS in the direction of nano physics. That's capital N means. It's a variant of UROPS. You're going to have a UROPS sharing after this. These are the new UROPS. We invent, now we have 4 types of UROPS. The regular UROPS without letter behind it, and UROPS in astrophysics, UROPS in nanophysics, and UROPS in quantum technology with A, N, and Q as a variance. So those are the UROPS specific in those direction. So this, there's a one warning about this, taking this minor and specialization, because if you are interested in this, you're probably going to do both. Okay, so in this case, you need to be careful about the module double counting issues. Each minor or each specialization, they are allowed 2 modules, 40%, to be double counted to another program. For example, you can use PC 1101, and you can use this PC UROPS to double count towards your major requirement. That's allowed. And you have these 2 modules. And then you cannot using this UROPS to double count towards your specialization, which is also including this UROPS. And also there's another module which is allowed in that specialization. So no triple counting is allowed, only double counting, and up to 40%. For minor, that's 2 modules. Okay, and for your major, second major, for example, that's 4 modules, etc. That's a NUS rule. It's very hard to override that rule. I don't know even it's possible. So when you do your study plans, don't put too much load on one module to fulfill 3 major 3 program requirements. I think that's about it for the minors. And any questions? All the old minors also been revamped because the used to be 6 modules, now only 5 modules. Some of them will have new modules inside because some of the modules are disconnected. If you are not freshman, the astronomy minor is also available to second-year student, but not the climate science, not the physics in technology. Those 2 minors are only for the CHS students. Is it advised to take computer science minor if I'm a physics major student? Sure, that won't hurt. If you like computer science and you want to do the minor, the minor will show up in your transcript, and that probably useful when you apply for a job. You see, not only you're taking those modules, you taking a specific. The minor is a basket of modules which design in particular direction. So yeah, I think that's fine as long as you can manage your timetable.
Hi, Xing Hai. I just like to check about the double counting that you mentioned just
Yes.
now. So let's say okay, for the senior batches, we took MA 1101 and 1102 as part of our major as well as faculty requirement.
Yes.
Can we use it to, let's say, count it to our math major or math minor? Let's say
Yes.
we'll take extra.
Yes, I think that one you can use one of the two, if I remember correctly. The 40% double counting rule is the current rule. But the old one, I remember many of our students used to be physics primary major and math secondary major. Yeah, MA 1101R or 12R, you can use one of them to count both.
All right, sure, thank you.
Double counting rule is roughly a general rule for 40% of any program.
All right, if there are no other questions, okay, we can move on to our next segment. But if you have any questions in between, you may just post it in the chat. All right, so moving on, okay, we have another senior, Xingni, who is a year 4 physics major. She is currently doing a minor in medical physics. So let's invite Xingni, okay, who will be sharing more about her experience as a medical physics minor.
Okay, hi. I don't look like that photo anymore. I've been worn down by 3 years, so that's not me anymore. Okay, so today I'll be presenting about the medical physics minor. It is, I think, one of the only restricted modules, minors in physics. So I'll just be sharing my slides. By the way, whatever information that is on my slides can also be found on the webpage. Yeah, so just to take notes. For those who are in year 1 or year 2 who want to take this minor, you have to plan carefully because some of the modules can be quite heavy. So you also have to, okay, I'll get to this. You know what? So first I'll start with some overview, the objective of this minor, how you apply, and the criteria for completion. So in general, the overview of medical physics is to inform you about the technology and how physics is applied in healthcare. And typically, whatever that will be covered in medical physics will cover diagnostic imaging. I don't think the physics modules will be super in-depth about the physics of it, but you just get a good overview on it and you have a good idea of how it works. And they go through some radiation therapy. Maybe it doesn't go through the therapies that I put in this point, okay? Just saying that this is the overview of medical physics. The actual module doesn't go through this stuff. I don't know this stuff. I should know this stuff. I don't. Okay, so the objective of this minor is to teach you the fundamental basics of medical physics. This minor will not be enough, and a lot of the jobs that actually like medical physics, I don't think whatever you study from this minor will be fully enough for you to be a full-fledged medical physicist. But it does give you a good background on it, and it gives you some insight on the kind of things that you will do as a medical physicist. So those who can consider these are like maybe you want to do research or you want to be a medical physicist. You can also go through this route because there are places that do accept fresh grads in physics. So I got this from the role here. I didn't take from out thin air. I took it from a job website because I'm always on LinkedIn and I'm always looking for a job. Okay, so I got all this from a website. I'm not lying to you. Okay, if you go for interview, then you tell them you know this the kind of shit that the medical physicists need to do. Okay, it's a lot of quality control, all this stuff, and the module does give you an idea of how radiation dose, but this is the role for most people, they start out not knowing what a medical physicist is or why a hospital even needs a physicist. So you probably need a physicist to tell you how much radiation you can be exposed to before you will die, I guess. So you need someone to regulate and check that you're not giving the patient more radiation that is needed for the necessary diagnostic procedures or for treatment, this kind of stuff. And for the academic and experience requirements, okay, SGH, I saw that SGH actually does accept fresh grads. If you have a medical, like physics minor, I'm quite sure that will be quite advantageous, but it will not be enough because they do want you to have some experience. So I think it'd be good if you can find an internship related to medical physics. And actually NUS does offer, I think it's a summer internship. So I wrote here that you can try to apply for the Chang Kung Institute for Radiological Research in Taiwan. So it is a 3-month program where you can go to Taiwan, you can work and study in the research institute. So actually that's quite good, you know, it does give you hands-on experience. And you should try that if COVID doesn't screw you over, but like by then. But for a lot of other places, it would be best if you can go for masters. And as Qing Hai has said, there is a need for these masters, but Singapore does not have these masters. So if you do fully intend to pursue this career path, you should be prepared to go overseas to pursue further studies. Yeah, just saying. Okay, so how to apply? The website online says that invitations will be, oh, yes?
Yes, I have a question. We do not have a master program. I thought we have it in the engineering side, do we?
I don't think so.
On medical physics.
Yeah, no, I think there were plans to carry it out, but I don't think there will be these masters in the near future.
I see.
Yeah.
That may be why this minor now being dropped by the engineering side. The way our department running this minor alone now. It used to be a joint.
Yeah, I think there were talks about it, and I have heard about it, but it hasn't been set in motion yet, or I don't know.
I see. Okay, thank you.
Yeah. Okay. Anyone have any other questions at this point? Okay, I shall carry on. Okay, so the NUS website does say that invitations will be sent to first and second year students, but if you don't receive the email and you still want to apply, you should email Dr. Chan. So how you apply for this is when you email him, I think Dr. Chan will ask you to write a short write-up on why you even want to pursue this minor. Sorry, I ate a lot. Okay. And then you need to prepare, show your module planning. Like you will be asked to prepare what kind of modules you take in your first year, your second year, your third year, how you are planning to clear this module, or whether your timetable even allows you to clear the minor. Because okay, very sad thing about this minor is that a lot of people do go into the minor, but not a lot of people complete it. Yeah, so I guess that would be the main worry like that Dr. Chan has. So you should go into it fully prepared lah. Yeah, so you need to plan out your modules, whether your timetable allows for you to take this module, when you can take it. And if you are a physics major and you have never taken bio before, you need to actually take the general bio module first before you are allowed to take the bio modules in that the minor requires. Yeah. So the criteria for completion, lucky for all the incoming students, that the minor requirements have actually been lowered from 6 modules to 5. But the same physics modules will have to be taken. So these are the 3 compulsory modules you see here: the GEH, the radiation lab, and the radiation for imaging. So yeah, I think there are no prerequisites, right, for the radiation lab and radiation for imaging.
Radiation lab have.
Oh, radiation lab have. Okay, radiation lab is.
It's currently 3232.
Ah.
Now it's going to change to 3295.
Okay, you know what? Just take all of these modules. Just you have to take it to complete the minor. You just have to do it. And just a word of caution: radiation lab even though they have lowered the requirement, it is still 2 long reports and 2 vivas. So the 2 long reports are 220-page reports. So do not try. You can try, go ahead, you can try, but I advise you do not take the radiation lab module hand in hand with other experimental modules. You can go ahead lah, but don't. Then for the GEH, it is very content heavy. Just because it's a GE doesn't mean it's easy. It requires a lot of memory work. And okay, but to be fair, it's a very interesting module. I found all of the modules that were taught in this minor, that were required by this minor, very interesting. This is, in my personal opinion, that I thoroughly enjoyed taking all the physics modules in this minor, because it really does show you the applications of physics in the medical field. And so if you want like a refresher, you want to take a step out of physics for a bit and look in how it's applied in real life, I guess you can go for this minor. PC3295 does regurgitate a lot of the content from GH1032. So if you take them both hand in hand, it's quite okay. Or you can take GH1032 before it, to prep you for PC3295. Yeah, that will be it for the compulsory modules. Yeah. For the electives, as a physics major, actually, I'm still currently doing some of the modules. I'm still clearing them. But yeah, if you're a physics major, please take your general bio mod before you can take any of these. Try to clear it early on. Yeah, don't leave it to the end. And none of these are SUable, just saying. And to reiterate Qing Hai's point about double counting, so for example, if you take radiation lab and you want to count radiation lab and radiation for imaging in your physics major, your GEH cannot be counted towards your GE requirements anymore. So you will have to take extra GEH.
I have to take GH.
What? Do you have to take GEH?
CHS.
Okay, you are lucky people. Just whatever. Okay. Yeah. What? Oh my goodness!
CHS also revamped the GE completely. Okay, yeah, you are stuck in between. We are also, because many of our GEs are being kicked out.
Oh no. Okay, then
the most popular one being kicked out.
Okay.
Yes.
Okay, good for all the oncoming people, but I would still strongly suggest that you take this. And there are a lot of very interesting physics GEs that you can take also. Just saying, just because the school says you don't need to take it doesn't mean you don't. You can. I mean, it's fun.
We are trying hard to either promote them to science inquiry 2 or interdisciplinary modules for those one being kicked out from the GE. But there are also GE remains which are not for CHS, unfortunately, but you can take it as an unrestricted elective. Like Xingni said, that many of them are really fun.
Yeah. Yeah, they're all, in all honesty, they're all quite interesting. So give it a try if you feel like you're up for it, For the biology modules, in my personal opinion, they are it's a different ball game from physics modules, and the approach that you take to them are very different. So yes, I'm emphasizing this for the third time that you should take the general bio module first and see how you take it, whether you are fit for it. Yeah. Okay. Also, when I went to search about the major requirements for the primary majors in physics, turns out you can totally not take any 4Ks if you do not wish to. So this won't really apply to you. But if there are certain 4Ks that you want to take, just to note that the 2-3Ks from this minor will not open up to any 4K module. So you have to keep this in mind if there are certain 4Ks you want to take that have prerequisites. Yeah, that is it for this minor. I think it's a very fun minor and it'd be great if you can join, and yeah, had a lot of fun in this minor. Hope you all can have fun in this minor too. If you have any questions, you can ask in the chat or you can unmute, you know. Okay, yeah, I'll stop sharing.
Well, while you think about your question, to add on one thing, I think from the chat, I got questions being asked about the study plans. If you want to take in minor, for example, outside of our physics department, they're basically infinite combinations or possibilities you can do. Then for those ones, you have to draw your own study plans because simply we cannot really provide so many combinations. We didn't even provide our own minors. Well, when you plan that, we make your plan slightly easier. We offer the first year and the second year compulsory physics modules twice per year now. So all those compulsory modules can be taken in SEM 1 or SEM 2. Some of them have a little bit of ordering. You want to take, for example, statistics after the quantum mechanics, not before. But we offer them in both semesters. So that will make you a more of freedom to make your study plans. The Faculty of Science required other departments do the similar thing. They may or may not have done it. So it depends on their manpower. For example, for data analytics, statistics department is not a large department by faculty member. They're huge now by student number. So they may have a difficulty to offer in both semesters. So when you make your study plans, keep that in mind. It's not saying I want to SEM 1 this, SEM 2 that, and SEM 3 that, then I'm done. And you realize this module, you want to take SEM 1 only offering SEM 2. And you're stuck. Okay, so any of those questions, you may contact me. For example, checking whether which module offering in which semester, and I'm more than happy to help you.
All right, thank you, Qinghai, Xingmi, for the sharing. Okay, so if you have no further questions, we can carry on to our next segment. All right, next we have Justin, who's also a year 4 physics major. He'll be sharing about his experimental UROPS on studying trapped states in organic semiconductors. So without further ado, let's invite Justin to continue the sharing.
Hello, everyone. Okay, so let me share my screen. Okay, so since I'm the first to go for the UROPS sharing, right? I think I should explain what UROPS is. So a UROPS is basically, you can think of it as a module, but what you do in this module is that you do research. So there's no fixed syllabus, there's no whatsoever. You just basically find a prof, discuss a research project with them, and then you do the research. So that is what a UROPS is. So it's a hands-on experience for you to get some research in your undergraduate life. So my goal for today is just one thing. Okay, I want to convince you that doing an experimental UROPS, or at least just a UROPS, is very, very good. I would recommend almost everyone who comes into, or everyone who comes into NUS to do physics, I will recommend you try a UROPS. So here's my goal for this presentation, and right now I'm going to go and share with you why. Okay, so where did I do my UROPS? So I did my UROPS in the Organic Nano Devices Laboratory. So my supervisor is Prof. Peter Ho. So Prof. Ho used to be one of the main people you will see in your time here in physics, but now because of the CHS, he's no longer teaching a module. But he used to teach thermodynamics in year 1. Just some picture to orientate you all around. This is Prof. Ho over here, standing next to the liquid nitrogen tank. It's unfortunately the only photo I have of him, so so you have to do. I was able to take a photo of the lab and put it here early on today, but then I was stuck in the lab the whole day. So enjoy this photo of a nice fireplace. But over here in this area is a petri dish of what are the organic semiconductors. So this is how they look like. They actually look like this. with the metal layered on top of the polymers and stuff like that. So, and this is me standing outside of the lab with my fellow researchers and Dr. Rachel, who is also from ONDL. Okay, so okay, what did I do? So what is my project? My project in my UROPS was basically studying trap state in organic semiconductors. So all these are pictures that were taken from the lab. They are not from Google or anything. So the organic semiconductors, and you can see right here is actually the machine of the O2 plasma, where we do plasma etching on the semiconductors and stuff like that. And this is how we test the electrical properties of the semiconductor by putting in this machine, then using the probes to kind of probe it. So yeah. Okay, so I am going to just give you a 1-minute crash course on what organic semiconductors are. Chances are 99% of y'all will not do a UROPS in organic semiconductors, and not 100% of y'all. Okay, but I think just to give you a taste of what I did for my UROPS. Okay, so organic semiconductors are basically, you have this thing called conjugated polymers. So conjugated polymers are just basically polymers with alternating single and double bonds. And because of this, right, because of the double bonds, you have this pz orbital overlap. And when this orbital overlaps, there are two energy states, okay? The bonding and anti-bonding energy states. And this anti-bonding and bonding, when you have a chain of them together, it forms the gap, the band structure. So in typical semiconductors, you have a conduction band and valence band. I don't know how many of you know this, but it's okay. They have a conduction band and valence band. Essentially now, the conduction band is what they call the HOMO, which stands for highest occupied molecular orbital. And then the valence band is the HOMO, and then the conduction band is the other way around, sorry. The conduction band is the LUMO, okay, the lowest unoccupied molecular orbital, okay? So the PZ orbital will cause this band structure. So basically, when you have this band structure, sometimes the polymers, right, because they are done using polymers, they do not have the perfect, they're not perfectly made. So the band gap actually has some energy levels, and these are what we call traps. And they can be desirable sometimes. Sometimes there are applications to these trap states, but most of the time they are quite a hindrance because they influence the behavior of your semiconductors in ways that you don't really want. So there are a lot of imperfections, and these imperfections, you might think that it's a fault of the experimentalists, right? They make the device wrongly, but sometimes it's just a inherent thing of the structure of the molecules, or the process in which you make it is always going to cause this energy level found in the band gap. Okay, so these are what we call trap states. And basically what I did to study these trap states is that I fabricated these organic semiconductors, and then like I vary the variables in these organic semiconductors, changing the polymers, changing the electron injection layer, the whole injection layer, changing the thickness of the semiconductor to see what affects the trap states or not. Essentially, that's a 1-minute crash course of what I did, okay, in my UROPS. But you are not here for that, right? Most of you are probably dozing off, whatsoever. Like, I'm not here for a physics lecture, right? Sure. So here, why do an experimental UROPS? Okay, first of all, my case for experimental UROPS is the fact that it's experimental means you get hands-on experience. You actually get to touch things and machines and make things yourself. All right. It's not something you get in everyday life, and even in your lab classes, you don't get to really, in your lab classes you have lab manuals and you just follow what the manual says. In this experimental UROPS, you really get to touch machines. Like literally some of the polymers cost like $10,000. Like a small bottle of them cost $10,000, and I get to hold them and I get to fabricate devices with them. It's like it's crazy the amount of hands-on experience you get to try and do for yourself. It's not something you can get in doing theory or computational, or even in just your everyday mods. Second, why should you do a UROPS? I think doing a UROPS really fuels your passion for physics. Like when you do physics, right? Every day you are just going for your modules and you're just learning the content, right? In a sense, sometimes you can get very disconnected from what the magic of what physics really is. Like, sure, you can look at equations on your sheet, on your piece of paper, and then you write and do questions, but you get really disconnected from what physics really is. right? So when you actually do the actual experiment, you are in the forefront of research. You really get to see, wow, this is what I'm actually working towards, and what I'm sure many of y'all will hope to do one day. Probably all of your optimistic physics year ones want to do research one day, right? Probably it's most of y'all lah. So next, you can really learn transferable skills. So like just now I said like, oh, just now the polymer layer is like $1,000, right? I get to play with it, $10,000 or whatever. Sure. You might think that then that skill only applies to that lab, right? But no, actually really whatever skills you learn in just being able to do lab work once is transferable to any lab. I think so in my time here as a year 4, I've actually been to 3 different labs to do research. And they are very different projects. Like I did my experimental UROPS, I did my UROPS in organic semiconductors, and I went out to do an internship doing research on cells, like cells, not like the batteries, as in like actual cells, like the biological cells and stuff. And like you find that the way you present your data, the way you speak about complicated topics and share your research with, let's say, your boss, or share your results with your boss, share your results with your colleague, working together in the lab together. Even analyzing data, presenting data, learning how to plot graphs, they are skills that you, no matter where you go, you need them. If you're doing research, you need them. Every lab will require you to plot graph. Every lab will require you to present your data in a nice and coherent manner. Every lab will require you to present your results to someone else. These are results that these are skills that you can transfer to any lab. And just getting in one lab, you find that when you're in the next, when you're working in another lab, you find that you're much stronger and much better than people who have never had lab experience before. And lastly, most importantly, is Xing Hai still here? He's not here already, right? Okay.
He left already.
Okay. Most importantly, is to get to know your profs more. Okay, because when y'all do your mods, y'all don't really get to. Some of y'all probably won't really get to talk to your profs. Right? Even consultation, sometimes you probably consult maybe the TAs or whatever. You don't really get to have one-on-one time with your profs. UROPS is really the time for that. And actually, if let's say you really want to pursue further studies, if you want to apply for certain programs, right? Sometimes even to apply for summer programs, you need letters of recommendations, right? And sometimes the way to really get close to your prof and to let them form memorable impressions of you, you have to be close to them and work one-on-one with them, right? And UROPS is really a good way for you to really get to know your prof and spend, hours and hours in the lab with them together, Yeah, so that's one good way one good reason why you should really do an experimental UROPS. Okay, now, my last point, why you should do an experimental UROPS. You can disagree with me, but purely, ultimately, physics is an experimental science. Yeah, sure. I can hear some of y'all like, oh, like string theory superior, whatever. Okay, but like, sure, you can think that. But ultimately, what makes physics a science is you have to test your theories. Here, you have to actually be in the forefront and check it out and see that it makes sense and see that it's really what we are seeing in the real world. What's the point of writing down equations to describe the world when you're not going to test them out in the world anyways, Okay, so some myths, all right? I'm going to dispel some myths because I can hear some of y'all lying on your bed, whatsoever, not interested in experimental UROPS, right? Not interested in experimental things. You all just want to be a hardcore theorist. That's fine and that's respectable, okay? But I'm just going to dispel some myths about what experimentalists can and cannot do. Number one myth I always get a lot is that people do experimental UROPS or people think about experimentalists is that they cannot do math or they cannot do theory. All you do is just sit in the lab and you do things, right? And sometimes people will tell you, if you are weak at math, then you should go to do experiments, go to the experimental route. I would honestly say that this is not true. Not because I think that experimentalists is the best thing ever. No, we are definitely not as good as theorists in coming out of the theory, okay, and doing our hardcore math. But the experimentalists must be very familiar with the theory. If you are not familiar with your theory, when things go wrong, you won't even know what went wrong. Like if your data is off, you won't even know your data is off because you don't even know what data you're supposed to get because you're not even familiar with the theory. When you receive data and it's telling you something opposite from what you're testing, only an experimentalist that is good in theory will be able to kind of predict what is a potential cause for that thing. Okay, experimentalists and theorists must go hand in hand. Like there's no one such thing as one is better than the other. Okay. And if you want to do if you want to be an experimentalist, you should really brush up on your math also and brush up on your own theory and make sure when you go into the lab, you know what's going on. Okay. Next, I know most of your physics majors and whatsoever, but doing an experimental UROPS or working in a lab has made me realize that actually the skills you learn in physics are not enough. Yeah, sure. Like a lot of us are very pure and whatever. We think that physics is like enough. But in my UROPS, when I went to go and do on semiconductors, I realized I need a lot of chemistry knowledge, like, you know, to synthesize the polymers and stuff like that, to understand why different chemical structures result in different properties. These kind of things, like, you know, when I was in JC, I hated chemistry and I genuinely thought I'd never use it in my life. Then now suddenly I realized I need so much organic chemistry knowledge and stuff like that. When I realized, but I only learned this when I'm working in the lab, I realized that now the world is more and more interdisciplinary and just doing physics is not enough. And even now in my FYP also, I realized I need a lot of like work on biology and understanding how cells work and stuff like that. The truth is sometimes the things you learn in physics is really not enough. And only when you when you go to the forefront of research, you realize that a lot of the skills you need, you cannot just get it from physics. You have to kind of branch out a little bit and be adaptable, right? And like I said this before, the things you learn in one lab, they apply to all labs. They are definitely transferable skills. You cannot just say that you learn one thing, then you don't, as you learn the things you learn from here, you will never ever use in another lab ever again. All right. Okay, so why so some of y'all might be thinking, actually, I'm not very interested in UROPS, or why am I'm not very interested, or I already know what I want. I know after I graduate, this is what I want to do. Okay, why should you try research anyways? I think the first thing is figuring out what you want is very important. I think it was, okay, as much as I'm trying to promote UROPS, it was only when I did research in the field of nanophysics and like nano devices that I realized that this is not what I want to do for the rest of my life. So sometimes it's like you think that this is what you really like, right? Like some of y'all go in and then y'all really think y'all really love quantum physics. But then when you really do research in quantum physics, you find that it's not your thing. And there's nothing wrong with that. So you will only really learn what you like when you try it and when you do it. Then you learn that actually, maybe I like something else, you know, that kind of thing. Or maybe this is really what I want. When I go to my lab every day, I feel like I'm filled with passion and I love what I'm doing. So then in that case, then you know, right? That's what you want. The next thing is really to expose yourself to stuff outside the textbook. The physics you learn in research, you'll never get that from a textbook. The ability to read research paper and read the new theories that are in the forefront right now, like theories that were published like last year, and then testing them out. You will never find that in a textbook. You will never learn that skill in a textbook, all right? And even if you're not interested in UROPS, I think it's a really good opportunity for you to get to know your profs, right? Okay, so what about some of y'all who maybe want to like feel that y'all have some spare time in after class and whatever, right? Or during the summer break? Actually, you don't have to do a UROPS to get research experience. Sometimes, right, actually, what you can do is that you see this prof and you see their area of research is something that you are very interested in. So I mean this in not just experimental way, in theory, for theory also, for those of you who want to do theory, right? You see this prof who does research in a topic that you're very interested in. Don't be afraid to hit them up. Like email them, ask them, hi, I'm actually quite interested in your research. Can I maybe, are there opportunities available in your lab? Then you can tell them it's not for UROPS. Maybe it's a bit of like a informal thing. Like every once in a while, can I just drop by your lab and just help you out with some stuff, or help you out with some experiments, help you out with some calculations, or even just emailing them and ask them, hey, I actually really like your research topic. Can we meet to discuss more about what you're doing? Don't be afraid to do that. What's the worst that can happen? The worst is that they don't even reply your email, or they say no, right? But actually, a lot of the profs, you find that if you email them and you ask them, can I actually try out some stuff in your lab? Can I try and visit your lab? Can I have a lab tour? Can I do an informal lab attachment? Can I work in your lab over summer? Can I just call to discuss your research topic? Actually, you find a lot of the profs they are more than happy to entertain you. So if you're year one, this is actually one thing I really which I learned when I was a year one. Don't be afraid to email your profs and ask them if you're interested in a certain topic. Just email the prof and ask, hey, actually, I really like what you're doing, and I want to learn more. They will, most of the time, they will entertain you. All right. So that's all. Hopefully, I convinced all of you to at least do a UROPS, if not an experimental UROPS. But that's all. So if you have any questions, you can hit me up at my number. You can text me. If you want to know more about my project, what I did, or the work life in ONDL, or in my other lab now, I'm currently in SIBA. If you want to know more about any of these things, you can text me or you can ask me questions after this. All right. Thanks.
Thanks, Justin, for the enthusiastic sharing. Yep. So now we'll move on to our next speaker. Okay, next we have our next speaker, Yuhua, who's a year 4 physics major as well. He'll be sharing about his UROPS on computational physics using microscopy image to predict magnetic properties of a material. Yep. So let's invite Yuhua to start his sharing.
So I'll be presenting for this part. I think it's supposed to be computational UROPS. So hope you're enjoying the talk so far. So let me go full screen. Okay, so I'm Yuhua, year 4 physics major. Very happy to be here today. So let me start by sharing what is a UROPS briefly. I think Justin has said quite a lot just now. So just some extra info. So this is all taken from the Science UROPS website. So basically it can be read as this is like a formalities. So it can be read as 2000 or 3000, depending on when you want to do it. And also it can be a year-long or just half a semester thing. I did a year-long one, but unfortunately only 4 MCs can be used to count for your graduation requirement from level 3. So because you have other level 2 mods and other level 3 mods, right? If you take a level 3, you can replace 4 MC from the level 3 graduation requirements. So the recommended time to spend per week is around 6 to 10 hours, which is roughly that for a 4 MC thing. But honestly, it's a variable. So it depends also on how much you want to put in the effort. So maybe if you're having a busy week, you will spend less time for this. And if you're having like more time to do work, and you can spend more, it's quite flexible. So the format is like you most of the time is you approach the professors to ask for a project. So the list of, there's no like official list of projects to see. So you have to check the physics department website, which I have over here is the staff websites. You can see like which topic the professor is working on. I think there's also a research handbook, but I'm not sure where is it now, that you can see all the like publications of the professor. So yeah, so this is roughly what is the UROPS. So here I share some pros and cons of doing UROPS, which is I think quite similar to Justin. So first, yeah, you can get to have some research experience. You know what you want to do or what you don't want to do, especially if you're going to do FYP or if you are going to attend grad school. So having some prior research experience is quite good. And also it's a networking opportunities that you can know more people, like especially maybe in the field that you are interested in. And also this is a good opportunity to like ask for recommendation letters, as Justin has mentioned. And also doing UROPS, you can learn things they are normally not taught in classrooms and textbooks, because all these are like the new things. They are not yet well studied, right? That's the whole point of the UROPS. So the cons, I couldn't really think of much cons. It's just that, okay, you take a UROPS and you have less time to do other modules. So maybe to some of you, this is a cons, but yeah, so that's the one disadvantage of this. So my general advice to the people who are interested in the UROPS is that first, you should have a well-defined project. Basically, you need to like talk to the supervisor and discuss what you want to do, and not like see how wait here and wait later, because these things, if you drag out, right, it's not a good idea. And don't like follow somebody without a plan. Make sure you have a clear like focus what you need to do. And second is you have to try to make time for the UROPS, because if you want to get good results, right, you need to spend some time on it. And I know this is quite difficult because with the full workload of other modules, yeah, it's hard to sometimes when, especially if your like deadlines are close, you need to still do this. It's extra commitment. So having good time management is important, which I think is also like general advice. And also don't get too discouraged if you like doing the UROPS, because firstly, the good results, right, is not like so easy to do, because after all it's a new topic, right? So people have not come out with successful. So if you are doing this, most likely other people have tried. And yeah, don't be discouraged because you have not gotten like results. So it's okay, yeah. And also secondly is that professors are like quite busy people, so maybe they will not like pay a lot of attention to you, and most likely you might go and work under not the professor themselves, but maybe like a postdoc or a PhD student. So it's okay, because these are also like professional people. They are qualified to guide you. So yeah, don't be discouraged if the prof never like give you enough attention. And also, it's okay to start with the simple task. So like maybe your first task will be to maybe write a program to talk to one of the equipment that you're going to use in your experiments. So it might be seems like a very simple task, but yeah, it's like you have to start somewhere. So doing these things, you will slowly get used to what's going on in the lab, and it's a like an ongoing process. So yeah, don't be too discouraged when you are starting out. The curve might be steep, but it's a part of the process. So don't be too discouraged. Okay, so now to talk a bit of my project is under assistant professor Anjan. So Prof Anjan is also has appointment in A-Star. So this is like a joint project between NUS and A-Star. So the project title is officially Estimation of Magnetic Parameters from Domain Images with Convolutional Neural Network. So this is a computational project, and maybe the title is not very clear what is going on. So I have helped you to put some images. So basically, magnetic parameters is something like Heisenberg exchange or anisotropy, which is property of some materials that we are interested. Domain images is a kind of microscopy image, which example is over here on the bottom left. And convolutional neural networks are a kind of machine learning networks. So it's a designed to do image recognition tasks. So this project has, I would say it's not really a physics project, but the physics part of this project is that you need to understand physics first before you do the project. But the project itself has doesn't involve quite a lot of physics. So yeah, so let me just talk a bit about what this project is about. So just some background information. I'll just be very brief about this. So if you have electrons, right, you might know maybe in quantum mechanics that the electrons actually have spins. So, and also atoms, because atoms have electrons, right? So some atoms have spin. If they do not add up like nicely, they might have spin. So in crystal, right, the crystal has made out of many atoms. So you can imagine like the spin is something like a little bar magnet, right? So physically you can imagine it as a rotating kind of electron, but actually that's not the real picture. But anyway, can think of this as a bar magnet. And if you have a bar magnet, right, you put a magnetic field outside, you will react to the external magnetic field. So like a compass. So the compass will point towards the north, right? So just something like that. So the spins, they will interact with external field. They also interact with like their neighbors. Yeah. So this is causing some interesting things to happen. And so in the crystal, right, most of the materials like salt, all this, we have a lattice of spins. So later I'll show you what they look like. So example, right, you can imagine spins maybe in 2D. I draw 25 of them here. You can have some arrows here. But let's say in a microscopy, right, in experiments, what do you see? You don't see little arrows. You'll see something like more like the color map. So in this case, right, pointing up will be something like black, and pointing down will be white. And if it's in the middle, it will be probably gray. So this is just a artificial kind of example to illustrate what you actually observe when you do the microscope on samples. So this is just a cartoon, but in the real life, right, what you see is okay, sorry, I just share some advertisement first. So these things are the interesting spin textures that you might actually encounter. So I'll just talk about the one labeled A. So this is called a skyrmion. So you see that outside the spin is pointing up in red and inside is pointing down. So these things are like very small. So the applications they have is that they can use in computing. So you can use it to store whether there's a skyrmion there or not. So you can see whether it's 0 or 1. So this can be easily controlled and it's very promising for next generation memory devices. Yeah, so a lot of research is done to convert this into real world applications. So just some advertisement. So there are other kinds of magnetic textures, but I will just not talk about them, just for you to see the different kinds of pattern that form. So in real life, right, how we see this pattern is using this thing called the magnetic force microscopy. So all this I'm sharing now, right, is not really actually my project, but it's like those required physics background that you need. So this is actually the physics part. So this is a magnetic force microscopy, and on over here you see like a tin sample. So basically they have this like little bar here which can sense the magnetic field created by the sample, and you can image out the spin textures. So for my project, what you see is images like this. So the length scale is like 1 micrometer. So I work with images that look like this. So just a background, haven't get to the actual project. So the question that I'm trying to answer, right, is given the image like this, are we able to deduce the properties of the material? So the things I'm interested in is in exchange, anisotropy, and this thing called Jaroszewski-Moria interaction. So they are just properties of the material. So how we do it? So traditionally, right, we can do individual experiments to determine these things. Like for exchange, we do some experiments. For anisotropy, we do some experiments. But this like very inconvenient to keep doing experiments, right? So we try to do other ways. So another way is that we use some techniques in image analysis, like Fourier transform the image and see whether, because the period of this image is related to some of these properties. So these are like analytical techniques to do it, but also not very reliable. So we want to do a very well-rounded way to get all the parameters that we need. So the way we do is using machine learning for this project. So yeah, so in the other direction is quite good, because if we know all the parameters, right, we can actually produce this image from just knowing the parameters. So there's this equation called Landau, Lipschitz, and Gilbert. I'm maybe some of you know who is Landau and Lipschitz, but yeah, this equation allow you to get actually the textures just by knowing the parameters. So I will show you some of these pictures later. So they can be implemented in like simulations to actually get some pictures, because to do all this machine learning, right, we need like a data set, and it's not easy to get this from experiment. So yeah, so in this project, I did a lot of generation of these images using simulations, and I trained a model to predict on these images. Yeah, so the general workflow is that we have a bunch of parameters that we're interested in, that we create all these pictures with different kinds of parameters, and we train like a machine learning thing to predict all these, and then we feed it with the actual experimental images, and we get the results. So that is roughly the workflow of this project. So as you can see, the physics part is actually in the front. So you have to understand the physics to do this. But when you do this, actually it's more like a machine learning project. So from this, actually, I learned both the physics part and the machine learning part. So it's I think maybe it is also relevant to know this machine learning, because nowadays a lot of these applications of machine learning you see everywhere on the news, right? So yeah, so if you are interested in, or maybe if you're interested in like skyrmions and stuff, you can also talk to Prof. Anjan. So yeah, so I think that's all for my section. Is there any questions?
There's a question being asked about which year will you advise the freshmen to actually take a UROPS?
Oh yes. Okay, I forgot to talk about that. Yeah, good question. So my advice, right, is to start as early as you can, because if you want to get good result, right, the longer you spend is strictly better for your chances to get some results. So, and especially if you are aiming to like have a publications, right, it's best to start as early. Even year 1 or year 2, you should already, like, even if you don't start the UROPS officially, you can already attach to the group and start to learn the things first. So when you actually do the work, you can do it quickly. So in my FYP, right, I have this student in year 2 who's already in my group. So yeah, I would advise you to start early. Yeah.
Oh, I got another question asking about, do you have any experience on machine learning before these UROPS?
Actually, I didn't learn anything about machine learning before. So yeah, so I picked it up during the UROPS. Luckily, my mentor has some experience with this, because my mentor also is actually a physics person, but he has some ideas on the concepts of machine learning. So he just direct me to some resources, but most of the time you have to like Google stuff and learn on your own, because people are also busy. They cannot like teach you everything. So you have to like be independent and learn, like willing to learn these things yourself.
Yeah, then maybe a quick question. What language, what programming language would you recommend your physics majors to learn if they're interested in computational aspect?
Actually, the language I use is Python. So I think probably a lot of people use Python here, right? So but maybe, yeah, I mean, if you depend on the project that you're working on. For me, I use Python, but maybe some people use like C++. So, but actually the language is like, once you know one language, is rather easy to pick up the other languages. So just try to understand the computational thinking aspect of it. That's my thoughts, rather than specific language.
Thank you, Ihua, for the sharing. So moving on, okay, we have our last speaker for UROPS, okay, on the theory. Rahul is also a year 4 physics major. He'll be sharing about 2 of his UROPS. One is the feasibility of a test of hidden influence inequalities, and another one is the equivalence of general relativity and parallel equivalent general relativity theories of gravity. So now maybe invite Rahul to start his sharing.
Okay, very good. So I guess I'm the last person out of the 3 to talk about UROPS. So and basically my job is to talk to you guys about why you should do UROPS in theory particularly, and the actual, like, the reasons for this are basically the same as what has already been mentioned. You want to learn, cutting edge physics in some very specialized area. Like, let's say you take a lot of modules, right? You still learn things only which were, in the 1900s. And even if you take, the level 5,000 modules, right, you still won't learn anything which is, contemporary and cutting edge. So Europe is pretty much the only way to do something of that sort. And also, if you want to see like what it's like to be a theoretical physicist, and I guess it's kind of self-explanatory. And also, if you want to see, you want to do theory, you want to do experiments, you want to try both, then it might make sense to do theory UROPS. And of course, also, if you want to go to graduate school in theory, especially, then I especially do recommend that you do a theory UROPS and also hopefully a theory FYP, because graduate school applications require multiple references. So actually, it can be quite difficult to find. As me and my friends know, it can be quite difficult to find three letters of recommendation from 3 references. So if you do UROPS, it's very good, because in that sense, it helps you prepare for the application process. Also, of course, research experience itself is good. It helps you stand out from other candidates, and etc. etc. So yeah, and as a side note, I would encourage all of you guys to do UROPS, because it helps you decide like whether you want to do physics as a career or not. Because if you want to do physics as a career, you basically have to do a PhD, and then a PhD is like 4 or 5 more years of your life. And I mean, like, if you don't know, if you're unsure about whether you really want to go into physics, right, you probably shouldn't do a PhD. And this UROPS will help you, think about, do I really like physics, or do I just like learning about physics? And they're 2 very different things. So yeah, because of that, I would encourage all of you guys, especially, to take a UROPS. And also, it's nice that it counts towards your graduation requirements. And if you're interested in theory, you might not be interested in a lot of the level 3K modules. So I guess it's good to do the UROPS. So yeah, first, maybe I'll give you guys a little background in quantum info. So So in normal information theory, right, like in computer science, you have bits, and bits are usually either 1 or 0, and then they represent they represent the fundamental form of information. And so, like for instance, in a physical implementation, right, you can have something like if a switch is turned on, then it's a 1. Then if the switch is not turned on, then it's a 0. So quantum information is very similar to that, in the sense that if you have zeros and ones, but you can also have something which is halfway. You can have an atom which is half the time in a 0 state and half the time in a 1 state. So that's kind of the basic reason for quantum information. And yeah, so in this example, we have 2 atoms, and one atom is in this 0 state, so it's kind of a 0 bit, and the second atom is in the 1 state. So I can also represent the whole thing as a single state, and I can say it's like something like a product of 0 and 1. You guys can see fine, yeah. Circle the thing. So you can see that the first one is in the 0 state, the second one is in the 1 state. So this forms a total state for the whole system. And so, I mean, you might have heard of quantum entanglement, but what it really is you have multipartite states with correlation. So this is a multipartite state because there are 2 parts. So multipartite just means many parts. Then in this case, you have 2 parts with correlations. So it basically what this picture shows you, right, is that if the A atom is in the 0 state, right, then the B atom is in the 1 state. Or if the A atom is in the 0 state, then the B atom is in the 1 state. And then we can write this out like this. The reason for the 1/2 is to show that it's with 50-50 probability. So this thing is usually the square root of 1/2. And the reason for that is because it's nice for us to calculate quantities such as probabilities when they're square rooted like this. So what my UROPS in this case was trying to establish is, are there any hidden influences which go from here, from A to B, like we go from A to B, which carry information that okay, this guy is in 0, so I must be in 1. And do these things travel faster than the speed of light? Because this, you guys know that the speed of light is finite, right? So if I separate these 2 systems by a distance longer than what the speed of light can cover, you can still see that these things are correlated. So is there some sort of hidden influence which is traveling and telling one guy what the other guy's state is? And if so, it'll have pretty profound implications, right? And the answer is theoretically no. And it's been shown that if you have some hidden influence which goes from here to here, right, like from A to B, then you can also use that to signal faster than the speed of light. So you could actually send information which is faster than the speed of light, which would be against relativity. I should note that this is quite a non-trivial statement, because you can have correlations but no possibility of signaling as well. So I'll just leave you with that. You can look into it a bit more if you are interested. You can look up something called no signaling probability distributions versus non-local probability distributions, and you can see that they're two different things. So my work basically was so there's a paper which shows that theoretically it's not possible. So my work is basically to theoretically design an experimental setup that verifies the results of the paper. So basically what I need to do is I have some sort of I can input a state of light, and I can put beam splitters and mirrors and things, and I can change the state of light. But what I want is an output state here, rho prime, which would violate a certain inequality. And you can think of this inequality as some sort of matrix inequality. So something like you have some matrix U, and then you want I don't know, U times rho prime to be less than something, less than 7. 7 was the number I had in my project. So and this one also must be rho prime here. So it's a scalar. Yes. Okay. So it looks something like this, and you have some sort of inequality, and only certain states will actually violate this inequality. So then basically my job is to come up with the setup in between. And yeah, so can we figure out what setup to use? That was what I had to find out. And unfortunately, it was pretty hard. So I could not come up with a complete solution for what setup to use. But we were able to rule out certain classes of setups. So, like I can make statements like if you only have beam splitters and phase shifters which only shift by like 180 degrees, then you can't do it and things like that. So I was able to rule out certain classes, but unfortunately this was harder than we thought. Work is still being done in this direction, and you can ask Prof. Valerie about it if you're interested. So some skills I use and stuff I learned. Of course, quantum information is the main thing that I learned. The concepts of non-locality, locality, entanglement, Bell's inequalities. And I did this UROPS right after QM1. So it was quite a jump for me, but with some work over the summer, it's very doable, I think. And Python, of course, in general, you will find that coding is a must in theory. So it's very difficult to get away with pen and paper work. You go crazy, doing calculations on paper. So please do use Python. There's a package called SymPy, which does symbolic computations. So do look into that. Also optimization in MATLAB. So in my setups here, I was able to, I let some angles be free, and then you can, so those angles can be, 60 degrees, 65 degrees, 70 degrees. And then you can kind of optimize over all these angles and see which ones violate the inequality. So that's something you can also pick up through this sort of a project. I also briefly want to talk about differential geometry. So that's the gravity. This is the second topic that that was mentioned. And I know a lot of physics majors are interested in this stuff, especially coming into uni. I did some interviews, and a lot of people were talking about this. We're talking about gravity and stuff. So let me talk also a little bit about this. General relativity is what we know. It's developed by Einstein, and says that if you think of this as your space-time, I mean it's 2D. Actual space-time is 3D. But if you think of this as your space-time and you put something on it, then the thing will bend and stretch, and then gravity is basically the motion of a particle in the stretched fabric, not really a force by itself. So there's no F equals to ma for gravity. It's just the space is curved, so if you let a particle be free, it will move along those curves. And so differential geometry is the standard way to study GR. It's a study of, differential, you can already think about it. It's basically the study of very small geometry. So quantifying curvature of a surface is done by something called the Riemann tensor. So things like that, it all comes under the umbrella of differential geometry. And it's a very natural mathematical formalism for general relativity. So TEGR is a competing theory of gravity. I won't say it's competing really, because at the current moment, both of them are kind of semi-accepted as, TEGR is semi-accepted as like a viable candidate for an alternative to GR. But so what TEGR basically is, it's called teleparallel gravity. What it says is that there's no more curvature. So you put a ball on your space-time, it doesn't change the curvature anymore. Space-time is kind of flat. And gravity is a force, and this force is because of something called torsion. And you can think of torsion as like an asymmetry in space-time. So your space-time is usually equipped with a mathematical structure called a connection. Then your connection connects points on your space-time from one point on your space-time to another point on your space-time. So if this connection itself is not symmetric, then it leads to something called torsion. And that torsion it can be shown that the torsion leads to a viable candidate for a gravitational force. And so my work is basically to show that whether these two are equivalent or not. So you show one way or the other that, if you start off with the TEGR equations, you can show the GR equations. If you start off with the GR equations, you can show the TEGR equations one way or the other. So maybe I can add a little. So what I'm doing right now is working out, because I think we have a candidate for a certain geometry where the TEGR and the GR equations are different. So we're doing a little more investigation into that to see whether we can actually show a difference there, and whether that leads to any implications. So skills I use. So this is a lot different. this is really a lot of pen and paper calculations. So I have a big logbook, and then I write, and I do, all this index gymnastics, move things around, and it just, a lot of things just have to be evaluated by hand. You can use Mathematica for a lot of stuff, and you should use it whenever possible, especially to calculate, things like if you're given a geometry, then the connection, for instance, can be calculated using Mathematica, but a lot of things just have to be done by hand. And I picked up a lot of differential geometry. For this project, I think PC 4248 and PC 4274, I think for your batch, it will be PC 5274 now, because your MM1 was split into MM1 and MM2, and MM2 was moved to MM3. This is the old MM3, so I guess it's the new MM4. And it was essentially a must for me to start the project. Then I spent the summer reading the remaining parts of the book on differential geometries. I have some of it. I can show you the camera. There's this book, so you can, yeah. And so some key concepts that you will pick up from this are bundles, connections, Lie groups, and Lie algebras. As for where these things are also useful, these are also very useful in statistics. I have a friend who's doing a PhD in statistics, and then we both are learning mostly the same things actually when it comes to the mathematical formulas. So in some sense, if you pick up differential geometry, and you want to switch to, I guess, statistics, probability theory, then yeah, then this is also applicable there as well. So okay, so some tips from experience. I think this is the most important part of my presentation. Please plan out your modules that you are prepared for UROPS, and take CS10 as early as possible. I would say take it in semester 1 if you can, or semester 2, because whatever project you do, you will have to do coding, and if you don't, if you're not comfortable at all with coding, it can be a little difficult, I think. So the earlier you do this, I would say the better. Also, it's just a very valuable skill in general. A lot of your normal modules, like thermodynamics and StatMech, you will have to do a significant amount of coding. So it's good to know to get the computational thinking into your system early. If you want to do a project in quantum info, I would recommend you do PC2130 as early as possible. Without knowing QM, you just can't do anything in QI. It just doesn't make sense to push QM and then want to do it if you want to do a project in quantum. Also, it doesn't make sense. And it's good to know some ST2131 is probability theory, and MA2101 is linear algebra. So it's good to know linear algebra and probability theory as well. It will be useful in your project. As for relativity, differential geometry, if you want to start early, you should start early. You should really do an early UROPS in year 2, or even year 1 maybe, and just learn the basics of general relativity, because by the time you take PC 4248 and 4274, it might be a bit late. You might be taking these in year 4, and it's already quite late to do a UROPS. So I would suggest doing an early UROPS just to learn the basics. Bonus is if you take something like MA3201, which is algebra. And if you want to read books on differential geometry, then it's good to have that mathematical background as well. But of course, it's not needed. And also, theory researches can be quite demoralizing. It's quite true actually, because things often don't work, and then you really only have yourself to blame, because I mean, you can't say that my program didn't work, or this didn't work, or that didn't work. It's really you couldn't do it. It can feel quite bad sometimes. So it's important to manage expectations and don't get disheartened too easily. Don't go into a spiral of, oh no, I can't do it, then why even bother trying? So it's pretty important to keep your expectations managed, under control. I mean, that's not to say that you shouldn't aim high or you shouldn't really try to achieve something good in your project, but it's just that if it doesn't work out, you also shouldn't get too despondent. Also say bye to your summers, because theory work requires a lot of background reading. So I spent basically my summer, last time I was interning as well, but I was also spending the evenings trying to read up some stuff, trying to read the book that I showed you guys. And it's good to spend your summers doing this, because then you're nice and ready when school starts. and you just cannot read like an entire textbook during the sem. It's just impossible. So yeah, and that's basically it. If you have any questions, feel free to ask. And yeah.
Rahul, I think when you want to show us the textbook, you want to show us on your video, right? But I don't think you turn on your camera.
Oh, my camera's on.
Yeah.
Oh, wait.
Yeah.
Is it on
So
now?
yeah, it's on now.
Okay. Okay. Yeah, this is the textbook. You guys can see it.
Maybe you want to turn off the blurring effect because it's
How did you know? Not yes. There you go. Yeah, I don't know how to mirror the thing, so but I mean the exact textbook is not very important. It's just you will have to do a lot of this sort of reading.
Oh, we have one question. Yeah. The person asking is if he have to take all these modules you recommended, and if yes, you do all the prerequisites.
The modules, yeah, I did all the modules that I recommended. Did I take all the prerequisites? Also, yes. So I took a lot of modules in my first 2 years. I learned a lot, which is so I think that's if you can if you are really wanting to do an early UROPS, then it makes sense to some extent. You have to be, but you should be careful not to burn out also, because you take a lot of modules, you have to do a lot of work. And yeah, I mean, it's easy to lose your passion for physics and this sort of thing if you're not. It's hard to enjoy yourself when you're under a lot of stress, even if it's something you like. So you should be a bit careful. Yeah, but yeah, I did do all the prerequisites. I think it's very doable if you plan your schedule out properly. And it's you can take a lot of. I would say it's very possible to take a lot of theory modules together, but do not take experiment heavy modules with in sems where you're busy, because EP1 and EP2 are disasters. It's really EP2 especially is a disaster. It's like 3 modules worth. So, but you can do I so basically I did all these modules in the prereqs. So I was able to do most of them by year 3 roughly, year 3 sem 2. So and I started my UROPS in year 3 sem 2. So this is kind of a late UROPS. But if you want to do one earlier, then yeah, it might be a bit impossible for you to do all these mods. So in that case, you can just learn them over the summer or something.
Yeah, one thing I might want to add in about the modules, I think Rahul used the old module codes that's applicable for the Faculty of Science, but I believe under CHS, all the module code has changed. So if you are referring to Rahul's module numbers, you might need to cross-reference it with the current modules to make sure that it's the actual correct thing that you are learning.
Yeah, actually, I should have been more careful with that. Yes, you're right. But I mean, it's pretty common sense. If you want to do differential geometry, then you should take the differential geometry mod, which is MM3, which is MM4 now, I think. And you should do GR, which is, yeah. And if you're doing QM, you should know QM. So, and linear algebra. You can always go and talk to a prof, and then he will tell you like what sort of mods you want to take if you want to go towards a certain direction. I know some of my friends asked, they asked Edward Gill, what mods are useful for a career in GR, and then he will like give you some suggestions. You can go with that.
All right. If no further questions, thanks Rahul for the sharing. Now let's invite the next speaker, Li Xuan, also a year 4 physics major. She interned at Systems of Silicon Manufacturing Company, SSMC. Okay, so maybe invite her to give her sharing.
Hi everyone, I'm Li Xuan, a year 4 physics major, and now I'm gonna talk about my internship experience at SSMC. And I don't know how many of y'all heard of this company before, but basically it's a company that makes semiconductors. So maybe you're thinking, what's the deal about semiconductors? Yeah, what's the deal about semiconductors? Well, if you have been keeping up with the news, then you probably know that because of COVID, there has been a shortage of semiconductors recently. And this is a global shortage. So why is it a bad thing that we are running out of semiconductors? It's because we use semiconductors in laptops, gaming consoles, and handphones. Even the newer technologies like the NUS Smart Bus and the virtual home assistant like Google Home also uses semiconductors. So basically, the smart future that the world is aiming for is going to use semiconductors. Yeah. So now what is SSMC's role in all of this? The semiconductor industry comprises of three stages, or three kinds of companies. The blueprint of the semiconductor chip is first conceptualized and created in the design companies. Then the design is sent to the manufacturing companies for them to follow the blueprint and then make the chips. And then they make the chips in bulk. Yeah, then the huge quantities of semiconductor chips will be sent to the packaging companies to be distributed to various clients for incorporating into various products like handphones. So SSMC is a semiconductor manufacturing company. Yeah, SSMC is actually a joint venture between TSMC and NXP Semiconductors. TSMC is actually one of the world's largest semiconductor foundry. It made the newest iPhone A14 chip, and it's also going to make the upcoming A15 chip for iPhone 13. Then NXP is originally the semiconductor division of Philips. So as an intern, I was tasked to shadow the process engineers. They were supposed to collect data from the fabrication equipment and analyze this data for anomalies. And examples of these data can be the scanning electron microscope images, or the thickness of the film, or the resistance of a film. Yeah. Then this is, so their main goal, the main goal of the process engineer, whatever they do, is supposed to improve the efficiency of semiconductor fabrication. Then apart from all those I just mentioned, they also have to test the new processes and materials before these new processes and materials can be incorporated into the fabrication process. Then apart from shadowing the process engineers, I was also given the opportunity to take on some projects like writing VBA for the automation of data analysis. For those who don't know, VBA is a programming language for Microsoft applications like Excel and Word. So you use VBA. So you can use VBA to automate the tasks you do on Excel or Word. Yeah. Yeah, I had to do that because SSMC analyzes a large amount of data daily. Because there's a lot of equipment manufacturing many chips every day. So from that, you'll get a lot of data from the that you need to analyze. And all of these data is critical in ensuring the continued operations of SSMC. I also had to do some data reorganization because a huge amount of data can be quite hard to visualize. And this was so that I could streamline data analysis for the process engineers. Yeah. So some of the skills I used and some of these skills which I think would be very useful for anyone who is planning to join the industry in the future and join any industry in the future are data analysis, VBA, Microsoft Office, like Microsoft Excel, Microsoft PowerPoint, Microsoft Word, and Tableau. Tableau is a kind of software that you use to make graphs from the data. Not just graphs, it can also be infographics or charts. So it's very useful to present the data in a concise way for people for like maybe the process engineers to just have one look at the data, then they understand what's happening very quickly. Then what I learned is, I gained understanding of the semiconductor fabrication process. Basically, the equipment and the process can be quite complex. So, for example, maybe this equipment needs to apply the titanium nitride film first, then it needs to apply another material film next. So there's a certain process to follow, and there's a lot of results that can happen. So it's important to understand the process. Then I also gain experience with real work projects, which can be quite different from school projects. For example, the timelines are stricter because delays can be costly. Then project scope is also stricter because if let's say the client suddenly wants to change the project scope, then the whole project, you will need to change a direction. And that can be quite costly too. And your quality of work is also very important compared to school projects because you have KPIs to meet and so on. And for the challenges I had, it was to take criticism. So one advice I have is to try to not take the criticism too personally, just consider it as a constructive criticism that you can use to improve on. And higher time pressure because of the deadlines of projects. And it was harder to communicate due to COVID. So the arrangement was that it was work from office at first, then it was work from home. So during work from office, you can just turn around and talk to someone if you have questions. But if it's work from home, you have to email people, or you have to send them messages, and they might take forever to see the messages. So yeah, it was quite challenging in that respect. And yeah, that's all. Thank you.
Okay, now maybe you can share about where can we find some internship opportunities, or what year is recommended to do an internship?
You can find internship opportunities on NUS Talent Connect, and you can also try, those job portals like those job portals that you can also use to find part-time jobs. Those also have internship opportunities. Then, yeah, what was the second question? I forgot.
Or what year would you recommend physics majors to take up an internship?
Actually, I think generally from year 2 onwards, you would have enough knowledge from your modules to take on an internship, because year 1 physics is a bit JC physics. So I feel that year 2 onwards would be good. For me personally, my first internship was in year 3. Originally, I was going to start in year 2, but then COVID happened, so it got cancelled. It got postponed. Yeah.
All right, then for your internship in semiconductors, did you find any of the modules useful, in preparing you for the internship?
I took a module called Thin Film Technology. It used to be called PC 4253. And I felt like a lot of the things I learned from that module was applicable to this, because my department was also called Thin Film. So it's basically the same kind of technology that was talked about in the module. But generally, I think any module would be good, because the basics you need, I feel, are just to be able to understand how the equipments fabricate the chips, right? So this one I didn't really learn in any of the modules. This one I just learned on the internship itself. Yeah.
All right, if there are no further questions, thank you, Li Xuan, for the sharing.
Thank you.
So now we have moved to the last segment, which is the Q&A. So if you still have any further questions, you may stay behind. If not, we have come to the end of this Zoom session, and I hope you really enjoyed, for both the senior freshman sharing, the student life portion and the academic portion. So if you have any feedback about the session, how can we improve for next year, feel free to just drop me an email, telling me, or just type in the chat, or just PM me, on how you think can improve. If you have any feedbacks. If not, that's the end of the session, and we hope to see you for any subsequent physics, physics activities.